All right, hello everybody. Welcome back to Math Background for ML. Today we're going to finish up with multivariate modeling, and then we're going to move on to linear regression. So let's get started. So if you remember at the end of last class, we ended off with talking about multivariate distributions, and in particular we had Gaussian distributions and copulas. And then we talked about maximum entropy in vector value distributions. And so maximum entropy in vector value distributions is in one sense exactly the same as it was for discrete and continuous univariate distributions. We've got a vector of features t, and each one of our features is a function of, in this case, all of our random variables instead of just one. And then the joint distribution of all of our random variables depends on the feature values through the functional form that we saw before, the exponential family functional form, which looks like this right here, right? And so it's proportional, it's exponential in t dot theta, where theta is our parameter. Just like the continuous and discrete cases, we can fit our parameter by maximum likelihood, which we can do by gradient descent. And you guys had an exercise doing that for a univariate discrete distribution. There are a few differences, however, between the univariate and the multivariate cases. So in the univariate case, this normalizing constant g of theta, right, or e to the minus g of theta, that's going to wind up being relatively straightforward to compute in the univariate case, because you're basically summing over all of the possible discrete values of your random variable, or integrating a one-dimensional integral over a continuous variable. And those are both things that we can do relatively accurately with reasonable amounts of computation. When we start to get to multivariate distributions, a multiple sum or a multiple integral can become much, much more difficult to compute. As a matter of fact, the computation can go up exponentially with the number of dimensions. And so max-ent distributions are still a very nice modeling tool, and they can be practical, but in order to make them practical, we have to think a little bit about algorithms for working with them. And those are not something we're going to cover in this course, with the one exception of Gaussian distributions. But if you go on in machine learning, there's a lot of different algorithms that you can use to make the computation reasonable. All right, so another thing that can be different in the multidimensional case is the connectivity of our features. Right? So each one of our features, say ti of x, in the univariate case, ti depends on, well, the single component of x. It depends on x. In the multivariate case, each feature can depend on some components of x and not others. So for example, you could have the first component of x squared, or the first component of x times the second component, right? And that's going to be we're going to call that a sparsely connected feature if it depends on only a subset of the features of the elements of x. And we're going to call the index set, so all of the xj such that ti depends on xj, that's going to be the neighborhood of ti. We'll write it like that. And that's going to become important when we get to graphical models. All right. So I talked about computation. Let's get to graphical models. So if we want to design a model for a vector of random variables, a joint distribution of several random variables, we can use a very general tool called a graphical model. A graphical model is actually quite strongly related to the ideas that we've covered so far, but it looks different. It has a new component to it. So in particular, it's got a graph, hence the name graphical model, that displays the relationships among our random variables. This graph is called the model structure. It's starting to get. Let's just take a look at our. Yeah. So sorry, while we wait for the comments to come up. We have, okay, this graphical structure. Oh, sorry, here we go. There's a, there's a question to go over the exercises. Absolutely. Yeah, I think it makes sense to go over them before we start on graphical models. So let me bring up the data files. So let's see if I can make some. All right. So I guess let's see. So what you were supposed to do is to take these data files, the two samples that we posted on Piazza, and try and determine what distribution they were sampled from. So let me load those up, and we can take a look. Actually, rather than loading them up, maybe it would be better for us to post some plots on Piazza, because it'll take me a second to make the appropriate plots. But let me just say how you could make the determination. What was the best way to decide what distributions they were? So the one of the samples, if you look at it, it was a discrete random variable. Right, so that rules out things like Gaussians to begin with. You can tell it's discrete because all of the samples were integers, which would be highly unlikely if it were a continuous random variable. And so you can look at our discrete distributions, and we had a bunch of different ones. For example, there was a Poisson, there were various Maxent distributions, there were power law distributions, and if you do a QQ plot between that sample and each of the various distributions, some will look like good fits and some won't. So the strongest, the closest wrong answer for the discrete file is probably normal, because the distribution happens to be fairly close to a normal distribution, except for being an integer and except for having slightly different tail behavior. And so if you made a QQ plot between this distribution and a normal distribution, you would see a gently curved line. And so remember, a straight line on a QQ plot means a match. And so a gently curved line means almost a match, not quite a match. If you made a QQ plot versus a Poisson distribution, you would discover a much better fit. You would discover a very nearly straight line. There would be some artifacts from the discrete nature, so you would have a plot that was stair-steppy with the stair steps at integer values, but it would be by and large a straight line. Now, in order to make that QQ plot, you would have to figure out which Poisson distribution to plot it against, because the Poisson distribution has a parameter, which is the rate. And so the rate parameter of the Poisson is actually equal to the mean of the Poisson distribution. So if you just set the mean of the mean of your Poisson equal to the mean of your sample, and try a QQ plot between a Poisson with that mean and the distribution estimated from your sample, you'll get a very nice match. All right, so that was the first sample. The second sample, if you look at it, it was continuous, right? So we gave it to you, I forget, to 3 or 4 decimal places, something like that, but the values were most definitely not integers. So it could have been something like a normal distribution, or a power law, or well, any of the ones that we showed. If you plot against normal distribution, this one should match very badly, because as it happens, it has heavy tails, which means that it curves very strongly away from the straight line, as the tail of the distribution gets much heavier than the normal tail. So so in addition to a QQ plot, one of the tools we suggested was a log-log plot. I actually happen to have that log-log plot up here. So this is what it looks like when you make a log-log plot. This is actually not exactly the same sample, but it's another sample from the same distribution. And so what I'm showing you is the log of the estimated CDF and the log of the, the log of X and the log of of 1 minus the estimated CDF. And so here you can see there's the red line is slope -1, and this is, in this upper left part, quite close to the line of slope -1. And the variance gets larger down here, right? There are many fewer samples as you get down to this part of the plot, because this is far into the tail of the distribution. But it's, modulo the noise, consistent still with being along this line. I think if you guys actually made this plot, it would have been an even better match to the straight line. I generated a different sample, which happened to be slightly less lucky than the sample that you guys have. So you would discover that it was on a log-log plot a very good match to a line with slope -1, which means it's a power law distribution with exponent -2, right? Because the CDF, the exponent in the CDF differs from the exponent of the distribution by 1. And so that's how you would determine, right? You'd make log-log plots and QQ plots versus a variety of possible distributions, and you would pick the one that led to the best match, meaning closest to a straight line on the plot. All right, so I hope that clears up what people were supposed to do for the exercise. If not, please continue to ask questions, and otherwise I'll go back to the lecture notes. All right, so graphical models. So these are a way to display the statistical relationships among all of our variables. They start from a graph called the structure of the model. And if you've ever seen people draw sort of informal circles and arrows diagrams that tell you what the relationships are among concepts or among variables, that's basically what this looks like. But it's a nice way to assign a precise semantics to graphs like that. So here's an example where we have 4 random variables: flu, fever, headache, and stays home. And the edges in the graphical model tell us what the relationships are among these variables. So in this graphical model, flu is related to fever and to headache, and fever and headache are related to stays home. So we're going to talk, there are many, many, many different kinds of graphical models. And we're going to talk about just one kind here called a factor graph. And the reason for that is A, that factor graphs are fairly general, and B, that they are really just a graphical representation of max-n, which we've already covered. All right, and graphical models, again, they can get really expensive when you get a lot of variables, but no matter what, They're a good way to think about relationships among variables, and also sometimes there are effective approximation algorithms. All right, so a factor graph looks like this. Looks a little bit different from the circles and arrows picture above. The circles and arrows picture is, if you wanted to interpret it as a graphical model, you would have to use a different type called a Bayes net, which we're not going to talk about here. So we'll talk instead about factor graphs. Factor graphs are hypergraphs, meaning that their edges can be adjacent to any number of nodes, unlike the standard sort of edge that are adjacent to only 2 nodes. Right? So you could have an edge between flu and fever, but you can also have a hyperedge that connects fever, headache, and stays home all at once. And we draw hyperedges with a little box that's connected to all of the nodes that it's adjacent to. All right. So we have a hypergraph, right? And what this hypergraph represents is the neighborhoods of the features in our maxent model. So you remember the neighborhood of a feature is the set of variables that it depends on. So this means that we have a feature that depends on both flu and fever and on nothing else. And we have a feature that depends on both flu and headache and nothing else. And finally, we have a feature that depends on fever, headache, and stays home and nothing else. All right? So the factor graph basically just shows you graphically what are the neighborhoods of all of your random variables. And it lets you determine graphical interactions between the random variables. So we'll say that 2 variables interact directly if they're connected by an edge or a hyperedge. So headache interacts directly with stays home and with flu. Flu does not interact directly with stays home. But we'll say that they interact indirectly if there's a path. So flu to fever to stays home is a path. And in this particular graph, all of our variables interact. But if there had been another variable over here not connected to any of them, we would say that that variable doesn't interact at all. Now, for the graphical structure, there could be a lot of features that depend on both flu and fever, and we'll only draw one of them. And that is for 2 reasons. Only drawing one of them doesn't change whether there's a path between nodes, and so we can still use the graph to determine these interactions. And the other is that the graph, of course, gets kind of busy if we draw 27 edges between the same pair of variables. And the other thing we can do is we can omit edges that are adjacent to just one node, right? So there could be, if we look at our, if we draw our graph here, right, we could have A, B, C, and D, right? And we could have a hyperedge like that, but we could also have a hyperedge just connected to D, right? And so this here, we'll just, this will represent the same dependence structure as this one, because we'll just omit that node for clarity. All right, so why do we do that? Why do we draw a factor graph to represent the relationships among our features in our maxent model? The answer is that it can help us answer properties about the distribution that we're fitting. And those properties are ones that we can then take advantage of when we're trying to get intuition for how to set up our statistical model. In particular, we're going to be able to figure out independence and conditional independence relationships among variables. And in particular, when the features are sparsely connected, that's when we're going to be able to determine independence and conditional independence relationships. If our features were densely connected, our graphical model would become a dense graph, a fully connected graph, and we wouldn't be able to get anything interesting out of it. So of the 2, independence and conditional independence, the simpler one is independence. And basically what happens is, so let's draw here an, sorry. So let's draw another couple of nodes over here, make a bigger graphical model, right, and say that they're connected like this, right? So two nodes are independent. Let's say it the other way around. Two nodes are dependent if we can find a path between them in our graph. So A and D are dependent because there's a path ACD. There's also a path ABD. But A and E are independent in our graph because there's no path from A to E. And you can sort of see how that would happen in a Maxent distribution, right? There's some features that interact with this set of nodes, variables, and there's some features that interact with this set of variables. But there's no features that couple those two groups of variables together. And so in particular, you're going to be able to describe your distribution as a product of two independent distributions. All right. So hopefully that makes sense, that you can use this graphical structure to determine independence. The other thing you can do is determine conditional independence. So conditional independence is a little bit more complicated. Just the question that we want to ask is a little bit more complicated. So in particular, we could ask something like, is A independent of the set D and E given the variables B and C, right? So that's an example of the sort of question we could ask about our graph. And what we can do to determine this is that we can again look for paths in the graph. So what we can do is the variables that we're conditioning on, we can shade them like that. And then we can look for a path from A to either D or E that avoids all of the shaded nodes, right? So in this case, there's no path, right? If we try to go, there was no path anyway from A to E. There are paths from A to D, but all of them go through shaded nodes. And so, in fact, this is true. This is true because there is no path. Now, if we had asked, is A independent of D and E given, let's say, just B, right? So what that looks like is we'll put C back there, right? And now there is a path from A to D, and so we'll say for this that it is false. The path ACD exists in the graph. All right. And so if you remember from our discussion of probability and random variables, one of the sort of intuitive qualitative relationships that you can have between groups of random variables is independence and conditional independence. And so what a graphical model does is it lets you design your distribution by describing what independence and conditional independence relationships you expect to hold, right? And the sparser your graph, the fewer edges there are in your graph, the more independence and conditional independence relationships we're asserting, and therefore the simpler our distribution is, the fewer parameters we're going to need to describe it. And that's good because few parameters means that we don't need all that much data to estimate the distribution. Now, I'm going to do an example of this in a second, but before we get to the example, I want to talk about one last thing, which is this idea called an accidental independence. So even in this graph, right, so this graph represents a Maxent distribution that has a parameter vector theta. And so even in this graph, it's possible that we could set theta so that A and D are independent. For example, we could put 0 weight on some of the features that, that are represented along this path. So that sort of independence that happens despite the graph structure is called an accidental independence, to distinguish it from a structural independence, which holds no matter what the parameters are, just given the particular graph structure that we've put together. All right, so let's do an example of a graphical model. And we're going to do a simple example which has 5 discrete random variables. We can be, it's going to be a graphical model that talks about the status of our robot. So our robot could be outside or not, meaning inside. It could be rainy outside. Depending on whether the robot is outside and whether it's rainy, the robot could be wet, right? And the robot could be made of metal or not. If it's not, let's say it's made of plastic. And if it's wet and it's made of metal, it could be rusty. And so we would like to determine what the relationship is among these random variables. We'd like to fit a probability distribution over these 5 binary random variables. So to do that, what we can do is we can build a factor graph, a graphical model. And so in particular, one thing that we could do is we could say, well, okay, these 3 random variables are connected to one another, so we'll draw a hyperedge. And these 3 random variables are connected to one another, and so we'll draw a hyperedge there, right? And so this is one graphical model that we could use to try and fit a probability distribution to observations of this sort of data, right? So let me, just to be clear, the sort of data we might get is outside, rainy, wet, metal, and rusty. So I'll put RA for rainy, right? And so we would get, maybe we would get an example of a robot that is outside, but it's not raining. The robot is not wet. It is metal, but it's not rusty, right? And then we might get another example of a different robot that's outside while it's raining, and the robot is wet. It's made of plastic, and it's also not rusty, right? And so we would, our data would be a whole bunch of examples, 1, 2, 3, and so forth, right? Where in each example we observe these 5 variables, and then we want to fit a joint probability distribution to all of them. And so we might try to fit a distribution that's described by this graphical model. Now this is not the only graphical model that we could use. We could, for example, so here's another one. We could say that there's a direct connections there, right? So this is a simpler graphical model because it's got hyperedges that touch fewer nodes, right? And then wet could be connected to rusty, and metal could be connected to rusty, right? And so these 2 different graphical models describe different sets of distributions, and we could fit either one of them to our data of this form. So I'm going to start pasting some code in here. Whoops. Start pasting some code in there, and we're going to start taking a look. So first, what I'd like to do is build a matrix of all of the possible feature values. So here is the matrix I'm going to build. And so this is a this is a matrix of binary numbers, right? So there's 5 different features, which are these 5 different variables. And so let's see, in the first 16 cases, I've got outside false. And in the second 16 cases, I've got it true. And then rainy, I've got true, then false, then true, then false, right? And this is all of the possible strings of 5 bits. So we can build that. I'll just show you the MATLAB code. It looks like this. We'll make that a lot bigger. All right, that should be big enough for people to see. Right, so basically MATLAB has this nice function called decimal to binary that turns an integer into a bit string. And so what I've done is just run that for the numbers 0 to 31. All right. Now, I generated some data from a distribution, which I'm going to keep hidden for now. But here is, whoops, let's keep that low. There we go. Okay, so there's some data, right? And so what I've done is I've assigned an integer to each one of these possible values, right? And the integer is between 1 and 32. And so, for example, 24 corresponds to the 24th row here, where we have outside, not rainy, wet, metal, and rusty, right? And so now I can build my, take that data and convert it into a vector of counts. So this function in MATLAB, what it does is it sums up the number 1 into the 24th component of counts, and then another one into the 24th component of counts, another one into the 15th component of counts. So what it does is it turns data like this into a vector of counts. All right, and so if you look at that, right, the first few elements of counts are going to look like this, right? And so dot, 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 right? So there are, for example, 3 samples of the number 3. Here's one of them, and here's another one, and here's the third one, right? So right, I'll delete that, but that's what it looks like. And now, what I can do is build a new, I'm going to build an augmented matrix of features. So here, this is my original matrix of features. The first 5 columns of this are my original matrix of features. And now I've created some new columns of features based on functions of the first 5 columns of features, right? And so, for example, this column number 6 here is going to be the logical AND of the first column and the third column, right? So you can see that in these rows, column 1 and column 3 are both 1. In these rows, column 1 and column 3 are both 1. And so this is the logical AND of those 2 columns, right? And each one of these other ones are some logical functions of other columns, right? And so I'm going to show you the code that does that. Right? Looks like this. Right? And so as I promised, I keep my features, and then I have the logical AND of the first and the third feature, and then the logical AND of the second and third, third and fifth, fourth and fifth. And so what I've done now, I'm going to use these features to build a maxent model. Right? And so I can draw the corresponding graphical model that goes with this maxent model. And so let's do that. Right? So my variables were outside, rainy, wet, metal, and rusty, right? And so feature 1 and feature 3, that's outside and wet. So there's a feature that connects, right? This column of my feature matrix depends on both outside and wet. So it's a feature that connects outside and wet. So I'm going to draw this hyperedge in my factor graph that connects those two original features. I've got another one that connects 2 and 3. So let's draw that. 2 is rainy, 3 is wet. I've got one that connects 3 and 5, so that's wet and rusty. And 4 and 5, metal and rusty. Right? And then I have my original features, right? So those correspond to factors that only touch a single random variable. We don't typically draw them, but I'll draw them just to be as clear as possible, right? And so this is the factor graph that corresponds to this set of features. And if we scroll back up, this factor graph is exactly the same as this factor graph, right? So it's one of the possibilities that I identified for a structure of a graphical model to model this data. All right. So now I can go ahead and I can try and fit this distribution to data. And so I've got some fitting code, which I'll go ahead and run. And so this fitting code should look familiar to you guys because it's almost exactly the same code that I ran to fit a univariate maxent distribution, right? So here we have 5 variables. In order to make the plot, I listed all possible values out along the x-axis. There are 32 of them. But it's not really one variable, right? It's 5 distinct variables, meaning that, for example, 16 and 17 are not particularly close to one another because their bit patterns are very different. All right, so this is what I've plotted here are all of the possible values of my 5 variables, and then the x's are the observed frequencies. So I never observed them all to be turned off at once. Whereas 3 times I observed them in the third possible configuration, right? Sorry, it looks like, yeah, 3 times. And then the blue dots are the fits to these. And so I've run code to do a maxent fit with a model of this shape. And I got a result, right? Which you can see is moderately close to the observed counts, right? So for example, in places where there are no counts, like this one, the estimated probability is lower, and in places where there are a lot of counts, like this one, the estimated probability is higher. All right? So stepping back a second, what have I just done? I've started from a set of 5 variables, and I've guessed what the relationships, what the statistical relationships are, what they could be between the variables. I used that to build a factor graph, which then I used to build a set of features for maxent, and then I ran some maxent fitting code to get a value of parameter vector. And so let me show you what that fitted parameter vector is. Here it is, right? And so in particular, so this one was feature 1 and 3. This one was feature 2 and 3. And so what these say is that you're more likely to have feature 1 and 3 turned on together, and you're more likely to have feature 2 and 3 turned on together, right? Which makes sense because outside and wet would tend to go together more often, and rainy and wet would tend to go together more often, right? So that's what the result of this code is. And now once I have this parameter vector, I can use it to make predictions. For example, I can have a new robot and observe, let's say that it's outside and it's made of metal, and I don't observe anything else. And then I could ask, what's the probability that it's going to be wet, given what I know? Or what's the probability that it's going to be rusty, given what I know? And I can use this parameter vector, theta, to try and figure out, to try and answer questions like that. All right. So let me go and put the Maxent code in place so that you guys can take a look at it. I'll erase the parameter vector that I learned, and here is the resulting, here's the code that I used, right? And so I initialize my parameter vector to 0. I compute the observed average of all of the features. And then repeatedly, I compute a probability distribution as e to the features times parameters, normalize it, calculate the mean value of the feature according to that probability distribution. Skip this is just for displaying. Then I calculate the gradient as the difference between the observed and the predicted features, and do gradient descent. And then this is just display code as well. All right. All right, so at this point, what we've done for the past few lectures is we've talked about a lot of different ways to model single variables, one at a time, and multiple variables, meaning the joint distribution of several variables. And the point of doing this is to be able to make predictions. So if you're just modeling a single random variable, the only thing you can do is predict what are the likely values of that variable the next time you see it. If you're modeling multiple random variables, you can also predict what's the likely joint setting of all of those variables, but you can also observe some of the variables and use that to predict what the other variables are going to be. And so that gives you a fair bit of power when you're trying to make predictions. All right, so please continue to ask questions if this isn't clear. And if not, we'll move on to the second set of lecture notes for today. So these are, as always, linked from the syllabus. The last set was the one that we were going over last class, last Wednesday. And here's the new set. So now we're going to move into regression. So what is regression? Regression is a conditional model. That means a model of the distribution of some subset of our variables, call them y1 through yd, conditioned on the remaining variables, say x1 through xp. And so the x's are called inputs and the y's are called outputs. And there's other names for inputs and outputs. Independent variables and dependent variables is the more statistical version of the naming. And we'll also call outputs targets or labels. All right, we can collect all of our inputs into a vector, And the same thing with all of our outputs. And so what we want to do is we want to model P of y given x. Now this is in contrast to the joint distribution, P of y comma x. And the reason we might want to make a conditional model is that we'll save ourselves the effort of modeling the distribution of x, right? So if we just need P of y given x, we can avoid modeling P of x and save ourselves some parameters that we need to fit this distribution. And therefore, hopefully that will mean that we can get away with using less data. And so this sort of model, P of y given x, is called a conditional model, as opposed to P of both of them, x and y, which is called a joint model. A joint model is sometimes called a generative model, meaning that we can generate pairs of x and y. And in the case that y is discrete, we'll call P of y given x a discriminative model, because it lets us choose between different values of y, meaning discriminate between them, given the value of x. So there are lots of different ways to make conditional models, and we're only going to talk about one of them, or we're chiefly going to talk about one of them in this course, which is a linear model. So the linear model is sort of what you expect, right? Here's x, the input, here's y, the output, and there's a linear relationship between them plus some noise. So y hat is our predicted y, and that's going to be x times w plus b, where w is the slope and b is the intercept. And estimating a conditional linear model is called linear regression. And this is the univariate case, where there's one input and one output. And we'll talk later about multivariate regression. Regression is useful because it's a very common special case of prediction, meaning that we have there are lots of other possible relationships besides linear, and there are lots of other models besides this particular model. But this is a particularly nice and interpretable one, and a lot of the intuitions that we get by looking at this one will hopefully carry over to more complicated prediction tasks. All right, so let's get started. So to fit a conditional model, we need a sample. Drawn IID from this joint distribution P of x and y. And this is exactly the same kind of data that we'd use to fit a joint model. The conditional model doesn't change the data we need at all. The hope is only that we need less of it if we're not modeling P of x. Or that we'll get a better fit if we can allocate all of our parameters to modeling the conditional instead of the marginal distribution of x. And so here's our sample, x1, y1 up through xn, yn. And just as a convention for this set of notes, I'm going to write the sample index as a superscript so that we can have both the, something like x73, which is the 7th sample and the 3rd component of that sample. All right, and we're going to, given that sample, we're going to minimize residuals. What is a residual? A residual is the difference between the true value of y and the predicted value of y. And what do I mean by minimizing them? I mean making them all small. But how do I trade off between making some of them small at the expense of making other ones large? And the way I do that is with a loss function. Loss function is just a function that is shaped like this, right? Meaning that it has a minimum at 0 and it increases as we move away from 0 in either direction, right? And so there's a lot of, different, that was supposed to have a minimum at 0, sorry about that. There's a lot of different shapes we could have for loss functions, right? We could have, right, something like that. There's a lot of different ones. We're going to use squared loss, meaning that the loss is just the squared value of the residual. But it's important to realize that you can sometimes achieve different properties by picking a different one. And so if we minimize the sum of squared losses, right, the sum, or the average squared loss, 1 over n times the sum from I equals 1 to n of the squared value of the residual, y minus y hat, where y hat is x times w plus b, right? So this average loss for squared, where a loss function is the squared loss. This average loss is called the mean squared error. and it tells us the variance of our residuals. Right? So because it tells us the variance, it's also common to report the square root of it, which is called the root mean squared error, and that tells us the standard deviation of our residuals. All right, so one common justification for using the squared loss is to suppose a linear Gaussian model, meaning that y follows a Gaussian distribution whose mean is x times w plus b and whose variance is some constant sigma squared. So that sort of linear Gaussian model, it does in fact lead to linear regression to least squares. Because if you look at the log likelihood, meaning the log of the probability of the y's given the x's, right, the normal distribution is e to the minus residual squared divided by 2 sigma squared, and then there's a normalizing constant in front of it. And this multiplicative factor doesn't matter when we're minimizing it because the variance is positive, and so we can just throw that away. And this additive term doesn't matter either because it doesn't contain the weight w or b that we're trying to fit. And so we can just discard this and discard that factor, and we're then still trying to minimize the sum of squared losses, right? And so Gaussian, this Gaussian model, linear Gaussian model, does justify least squares. But it's really important to remember that this is not the only possible way to justify least squares. Least squares actually make sense a lot more generally than just in the linear Gaussian model. In particular, anytime we would like y hat to be close to y, then least squares tries to achieve that. And in fact, it typically succeeds. You can actually prove that in the limit of having lots of data, least squares will converge to, in some sense, the best possible model, the one that actually does minimize the expected squared error of our predictions. And the reason this fact is important is that it's very common to use linear regression even when the conditional distribution of y is very clearly not Gaussian. For example, y could be a binary random variable, and it would still make sense to do linear regression. So it's important to know that there is this justification, and it's a common one, but it's not the only reason to justify linear regression. All right, so we're going to go ahead and we're going to try to analyze least squares and linear regression in the univariate case. Before we do that, I want to make an assumption. And that assumption is what's called centering. So centering just means that the average value of the x's is 0 and the average value of the y's is 0. And we can achieve that without loss of generality by just subtracting the average value of x from each one of our x's and subtracting the average value of y from each one of our y's. And centering is nice because it lets us avoid having an intercept in our linear regression. This is not necessarily true for general models. In general, you don't always want to center your data, but if you're doing linear regression, it helps with interpretation to center it because you can just get rid of the intercept. And to see why, I'm not going to go through this in detail, but if you differentiate the sum of squared losses with respect to the intercept b, you'll find out that the derivative is just proportional to b, and so in order to set the derivative to 0, we have to set b to 0. Right? So, and that this derivation assumes that our data is centered. So if our data is centered, we can just drop the intercept term b. Now, of course, it is if you're actually going to make predictions, right, it's important to undo the effect of our preprocessing. So if we make a model that says y minus y bar is equal to w times x minus x bar plus a residual, well, we actually want to predict y, and so we can just move all of the bars over to the right-hand side, and we get y equals xw plus this constant term plus our residual, right? And so here, we can just set our intercept to be y bar minus w times x bar, and we can make predictions just like we would before, right? So we would like to make predictions based on x, not x minus x bar, and we would like to predict y, not y minus y bar, and we can do that just by adjusting our intercept. So we've removed the intercept to make the math easier, but we can put it back very easily. All right. So now let's look for the value of slope that minimizes squared error. So in order to do that, I'm going to collect all of my sample into a big vector, x1, x2, all the way to xn, right? That's my inputs. I'm going to collect all of my outputs into a big vector, y1 up to yn, right? And then my loss is equal to 1 over n times the squared norm of y minus x times w, right? So w here is just a scalar. I'm multiplying the vector x by that scalar, subtracting from y, squaring the result, and then averaging, right? I can write that as well without the norm sign, 1 over n y transpose y minus 2 y transpose x w plus x transpose x times w squared, right? And I can take the derivative with respect to w, right? dl is equal to 1 over n. The y transpose y goes away, so I have minus 2 y transpose x dw plus x transpose x, and then the derivative of that is 2 w dw, right? And so if I collect terms, I get, if I want to set this, I set this equal to 0, I get that 0 equals, I can just drop the factor 1 over n and the factor 2, so I get y transpose x dw with the minus sign plus x transpose x w dw, right? And I can drop the dw as well, because in order for this to be 0 for all possible values of dw, the coefficient of dw has to be 0, right? So I get then that w is equal to y transpose x over x transpose x, right? And so this is just a simple expression for the optimal slope in a linear regression. And okay, it's an expression, not really immediately obvious how to interpret it. And so what we're going to do for the next little bit is work on interpreting this. So the first thing I'm going to do, I'm going to put back the factor of 1 over n in both the numerator and denominator. That's not, that obviously doesn't change things. And so that's equal to, well, the denominator, that's the sum of the squares of x divided by n, so the average squared value of x. That's also called the variance of x, right? And here, this is the average product between x and y, which is called the covariance between x and y, right? So this is slightly more interpretable. The optimal slope is the covariance between x and y divided by the variance of x. We can actually go a little bit farther by noticing that scaling x and y changes the regression in a predictable way. So here's our regression to start with, right? So x and y. If we double y, it doubles the slope of the regression line, right? And if we double x, it halves the slope of the regression line. And you can go through and you can prove that by looking at the properties of variance and covariance, but really it just sort of makes sense. If you double y, then your prediction of y should be twice as large. If you double x, then you have to have the weight in order to make your predictions of y stay the same. All right, so because we can do that scaling, we can scale so that x and y both have variance 1. And in that case, right, so let's go back here. let's leave that like that. And we'll say here we've scaled so that variance of x is equal to variance of y is equal to 1, right? Then variance of x goes away, and we just get w is equal to the covariance of x and y. But the covariance, remember that the correlation of x and y is equal to the covariance of x and y divided by the square root of the product of their variances. Right? So this term is just 1 because we've assumed x and y to both have variance 1. So this is the same as saying that w is the correlation between x and y. So this here is maybe, to me, the best way to interpret a linear regression. In particular, what it says is that if x and y have 0 mean and unit variance, then the regression line has just slope equal to the correlation between x and y, right? So the best fit line just depends on their correlation. If x and y do not have unit variance, then we can just scale the correlation to compensate for the variance of x and y. So in particular, if you increase the variance of y, then you increase the slope, and if you increase the variance of x, you decrease the slope. And we also talked about how to handle non-zero means. You wind up just changing the intercept to compensate for the actual means of x and y. So there's a question about the difference between covariance and correlation. This is something that we, if you want to review it in detail, you can go back to the notes on probability from the near the beginning of the first mini. But just briefly, basically covariance confuses two different things. Covariance tells you both something about how x and y depend on each other and how large x and y are, right? So you can make the covariance larger by scaling up either x or y. Correlation corrects for the scale of x and y, right? So it corrects here, it takes the covariance and it divides by the square root of the product of the variances. And so what that means is that scaling up x or y does not change the correlation, right? And so correlation separates out the effect of the dependence between x and y from the other thing that covariance talks about, which is the relative scale of x and y, right? So if you, maybe we can draw a picture, right? So here's x, here's y. If we have x and y sort of tightly coupled around, tightly clustered around a line, right? This is high correlation. Whereas if we draw the same plot, x and y, and they're sort of much more widely distributed around a line, this is low correlation. Whoops. All right. And the sign of the correlation tells you whether the line has positive or negative slope. So these are both positive correlation. We can draw, for example, this would be very negative correlation. So I'll write that as strong negative. Right. And here, I guess instead of high, I'll be more specific. I'll say that this is a strong positive correlation. Right. And I've drawn these plots without scales. because correlation doesn't depend on the scale of x or y. But we can alter the covariance by just taking this and changing, like multiplying y or x by a constant. So we could make the covariance be as small as we want by multiplying y by something like 10 to the minus 7, right? That would leave the correlation the same but make the covariance very small. Or we could make it much larger by multiplying y by 10 to the plus 7. The correlation would stay the same, but the covariance would get very large. All right, so that's covariance and correlation. And just to recap, right, the regression line is a fit whose slope is the correlation, but then it's scaled to compensate for the actual variances of x and y if they're not 1, and it's shifted to compensate for the actual means of x and y if they're not zero mean. Right? So that's basically the interpretation of univariate regression. And we will, at some point, probably give you guys some exercises to let you play with regression. But I think possibly we may wait until we discuss multivariate regression because that's more fun to play with. All right, so in the last bit of class, I want to talk about the problems that we can see with linear regression. So there's a bunch of problems you can get, but the three biggest, most common problems are outliers, heteroscedasticity, and nonlinearity. So nonlinearity, I guess it's pretty obvious that nonlinearity would be a problem for a method that's called linear regression, and in fact it is. The other two are maybe a little bit more subtle. So outliers means that the distribution of residuals is heavy-tailed, meaning that there could be a few residuals that are much, much larger than all of the others. And these points with very large residuals are called outliers. So to be clear, an outlier is an extreme value of y, the output, compared to what we'd expect. And it's not an extreme value of x. You can have a very typical value of x, but an extreme value of y, and that's called an outlier. Or you could have a very extreme value of x, but if the value of y is typical, that's still not an outlier. Now, outliers, unfortunately, can dominate. They can really mess up the output of least squares. And you can sort of see that by looking at the equation, right? We want the derivative of the loss, total loss, or average loss with respect to w to be 0. And that means that the sum of the derivatives of the individual losses for the individual examples should be 0. And if zi, the residual on the ith example, is large, well, the derivative of z squared is proportional to z, and so large values of z lead to large derivatives, and so all of the other terms have to compensate a lot in order to make up for one really large residual. All right, so that's outliers. Even if all of our conditional distributions are Gaussian, it could happen that their variances are different, and that's called heteroscedastic. And these differing variances, right, so let me go and draw, right, so here we have some points and we have a line, right, and that's our linear regression fit. If we then have, let's say, another point down here, right, so this is going to be an outlier because it has a very large residual, and in fact it's going to change our regression fit to be something more like that. Right, and this here was the fit without the outlier. Okay, so heteroscedasticity looks a little bit different. So here's our regression line, and let's say over here we have some high variance points, right, and then maybe towards the middle we have lower variance points, and then maybe towards the end we have that's too far down. Maybe over the end here we have some higher variance points. So this is heteroscedastic. Because we have high variance here and here. but lower variance here, right? And the same sort of thing can happen with heteroscedastic fits. Basically, these areas with high variance will wind up dominating the fit because it's really important to get the large residuals to balance out. And then, of course, if you have a nonlinear relationship between x and y, sometimes you can still get qualitative properties like the overall average direction of the relationship, but life would obviously be better if we took account of the nonlinearity. And so nonlinearity, it's useful to know that it can sometimes look like, because if the true value of the true expected value of y given x, it could get closer to or farther from the best linear model, and when it's close, the residuals look smaller, and when it's far, the residuals look larger. So to diagnose problems with the linear model, in particular those three, it's often a really good idea to make what's called a residual plot. So a scatter plot of prediction on the horizontal axis versus the residual on the vertical axis. And here, for example, we're showing a clear problem, right? So our residual plot should look like, oh, sorry, this is not the residual plot. This plot, I'll change that after class. This plot is a plot of the independent variable versus the residual. The residual plot would look something like, well, you would just subtract off this prediction line, right? So it would look like this. Right, and this is y hat, and this is z. Okay, and so the residual plot, it looks like a curve instead of a straight line, and that's evidence that there's a nonlinear relationship between x and y. It also has some outliers here, right? So here's a point that's very far from the best fit line, and so that's potentially a problem. And in fact, it also looks heteroscedastic, right? The variance in the middle is larger than the variance at the ends. And so, this example is a regression gone bad, and we can discover it by looking at the residual plot. So how do we fix these problems? Well, we can fix outliers in a couple of ways. The first is to use what's called a robust loss function, meaning a loss function that doesn't depend so strongly on large residuals. And two of those are the absolute loss, meaning just the loss is equal to the absolute value of the residual, or the Huber loss, which basically looks like the absolute value when you're far from 0, and it looks like x squared when you're close to 0. So this is Huber. And these loss functions help deal with outliers because their derivative stays bounded even as the residual gets really large. Now, it's not quite as efficient to minimize Huber loss or absolute loss as it is to minimize squared loss, but it turns out that there are still efficient algorithms to solve the problem. The second way to deal with outliers is just to get rid of them. And getting rid of them means we have to find them, but it turns out that there's a very simple heuristic that can often find them really easily, which is to fit a line to all of our data and then look at the residuals and assume that the few largest ones of these residuals are probably outliers, drop them, refit the line. And now we've changed the residual of each point. There are some new ones that are potentially large, so we drop those and we keep on going. And as long as the initial fit was sort of halfway close to being right, then we'll be able to identify the worst outliers still from the initial fit. And then when we drop them, our fit gets better, meaning that we're better at identifying and dropping outliers, and then our fit gets even better, and we drop a few more outliers and so forth. The last thing that we want to do is potentially fix heteroscedasticity or nonlinearity, and basically what I'm going to do is punt on those until we get a chance to talk about multivariate regression, because the best fixes for those are adding new features and adding new feature transforms, and we can't do that until we get to multiple regression. All right, so that's everything I wanted to say about univariate regression, and also the graphical model example. So I have office hours now. Unfortunately, today I have to end them at 3:30. So please go ahead and ask us questions, and we'll see you next time. Thanks.